Okay, you good, good.
Well, welcome, folks. We're going to give a talk today about software-defined radio. My name is Derek Kozel, MW0LNA, and I've been working professionally with software-defined radio for the last 15 years or so, ever since I was in undergraduate. And it turns out that one of the founders of some of the SDR hardware that I'm going to talk about was a ham, student ham in the club that I was in. And he, as an alumni, had donated a software-defined radio to us even back then. Since then, I've worked professionally and as a hobbyist in this space, and GNU Radio has been a tool that I've used quite a bit. So what is GNU Radio? We'll get into that, but I have a bit of a challenge for you starting out here. So there's this article called 50 Things to Do with SDR. I think it's a great introduction as it doesn't require a license. It's something, quite a few of the bits you can do completely for free, just downloading free software and trying things out. Or you can buy an RTL SDR, which I'll show you in a minute what that looks like. But this is a nice, cheap radio receiver that you can use to explore the wireless world around you. Try out SDR++ or another receive software, and then go underneath the hood and actually try making something custom. I like to call this digital home brewing. And if you want to take a look, there's a talk by me basically on all of this called digital home brewing that I gave at the RSGB convention a couple of years ago. So this is my goal, that at least some of you will go out and do this after the talk. So what's the broad context here? We've reached a point in the technology curve where things that weren't possible before now are. You can get cheap off-the-shelf hardware and control one of the four fundamental forces of the universe. The electromagnetic spectrum really is something that's quite unique in our ability to modify it. And the fact that we as hams and everybody has access to spectrum, in the instrument, scientific, and medical bands, we have access to unlicensed spectrum that we can not only receive, but we can transmit in, albeit at low power. So with this, we have the ability to actually start exploring these things. Now, where does that go? Here's some examples of things that have been done. The SatNOX project is this distributed network of satellite ground stations, all running on software-defined radio. So very simple hardware, open source designs, some 3D printed parts, and you have a satellite ground station that you can use. Now, taking that same radio out and popping it into something else, you can download satellite imagery, and this is real time. So you can actually see it before the weather, the people doing the weather predictions have even seen the images. I should really get a cup of water here in a moment. There was a fun project a number of years ago at this point where a satellite had exceeded its operational lifespan and had flown out into space. Its particular orbit took it way out beyond Earth's orbit. And at some point, it looped back around and it came and did a flyby of Earth. Now, NASA had finished the mission. They passed it off. And so a bunch of amateurs, both literal amateur radio operators and just hobbyists, put together some commercial off-the-shelf gear, researched what the radio protocol was, went down to Arecibo before it was destroyed, unfortunately, and they were able to actually send uplink commands to that satellite using just GNU Radio and open source software. They were able to actually get that satellite started back up, receive a bit of telemetry from it, and there's some great talks online about how that works. Amateur pulsar detection. If you're interested in radio astronomy, this is something that you can pretty much go into your down to like B&Q, grab a couple of parts, put together, a plywood and tinfoil horn in your backyard, and start receiving pulsars. Right around 408 megahertz is a really nice frequency range for doing that. And there's open source software for receiving those signals. And the nice thing is, even something like an RTL SDR is actually sensitive enough to be able to do it if you build up the system enough. The Virginia Tech University in the United States has a ground station and sounding rocket, and they run GNU Radio both on the ground and on the rocket. Also, not in this deck, but Planet Labs is a company that launches small satellites into low Earth orbit, they're CubeSats, and they're taking imagery of the Earth continuously. And all of their radio downlink runs off of GNU Radio as well. So this is a tool that really does scale, and it's amazing that we get to use it for free. In cybersecurity, software-defined radio gets used quite a bit because, as we'll see, it gives you the ability to work with a radio system right down at the bare bones. It's kind of like taking a soldering iron to the protocol, to the waveform. You can really get in there and work with it and break assumptions that manufacturers have put in place. They've said, we're going to build our own chip. This is our own black box. It's got an external connector, and nobody's ever going to be able to work with our waveform. But it turns out that we're able to receive that, start looking into it, and get quite deep into it. So there's a lot of great examples of everything from tracking like tire pressure sensors on your car, all the way up to temperature sensors if you've got a home weather station, radio sondes which get launched up into the atmosphere, and you can actually start receiving some atmospheric data that way. And there's a lot of interesting moving pieces there. Yes, don't actually go and seize control of wireless infrastructure, but it has been demonstrated. And this is something that a lot of groups will do, both here in the UK and abroad, to show that these manufacturers need to step up their cybersecurity demands. And part of our responsibility as amateur radio operators is to provide some of that skill force of educated radio people. And so I think that it's really important that SDRs be brought in, early on in people's amateur radio careers, because this is the technology that a lot of things are running on, and it's available at a really low cost. The fact that we get to play with it is just amazing to me. I'll keep on saying that again and again, I'm sure. You can also get fun things like this, where just listening in with your RTL SDR, like next to your laptop, if you're tuning around, you might notice some RFI, some unintended emissions from a laptop that's actually carrying like modulated microphone audio. This was a case a couple of years ago with a bunch of HP laptops. And you could actually see this modulated up onto a power rail. So they had some switch mode power supply at 24 megahertz, and it was actually mixing the microphone audio onto it. Passive radar, this is another fun one. If you've ever looked at airplane scatter or meteor scatter modes, this is basically doing exactly the same sort of thing. You have somebody else transmitting a radio signal, and you're looking for the bounce off of it. But with an SDR, you can do more than just say, oh, that signal has appeared, but also what's its Doppler shift and what's the delay between the signal arriving directly to me and the signal bouncing off of something like an airplane. So more tools and more software that are available out there. So what's GNU Radio? Hopefully that's the motivation for why this is interesting. I won't run through all of this, but this project's been going for almost 25 years at this point. It was originally started as a simple demonstration. Let's build some digital signal processing that could use hardware that didn't even exist really at that point or was very expensive, and start implementing it. It gets shared out online, and people rapidly start adopting this. And some of the first people who get involved with this are hams. It's originally funded by John Gilmore, who, if I remember right, is G0 GNU. Eric Blossom also, I know, has his license, and Matt Edis, we'll see on the next slide, has his. And this has continued to the present day, with many of the contributors and leads of the GNU Radio project being hams. We've been hosting a conference every year since 2011. The videos from almost all of those are up on YouTube and are just a great library of talks showing both the cutting edge of radio research, what's happening in industry, and a whole bunch of individual projects by hobbyists, by students, and by working professionals just trying to get something done in the lab aside from their main work or to facilitate their main work. So I love to throw this in. So this is Matt Edis, N2 MJI from the United States, who showed up on the GNU Radio mailing list and said, man, we really need a common piece of hardware for this, something that isn't a couple of dev kits pulled together that everyone had to build themselves. Let's get a standard piece of hardware that people can get, experiment with, and have a common platform. Uh, and he put this email out saying, this really isn't that hard. And about a month later, nobody had really responded saying, yes, let's do this. Let's put it together. Here's a plan. And he came back and said, yes, I'm doing this now. And that was the birth of a company called Edis Research, which ended up building the Universal Software Radio Peripheral, USRP. And the disclaimer is I ended up working there. He was he was a former member of my undergraduate university amateur radio society. And it was amazing to get to go work there after university and be involved with building some of these radios. And hopefully, as part of either today or Thursday, when we do the second half of this, I'll show off some of the wide bandwidths that we can get with those radios. So I'm conscious of the time. I will kind of keep rolling through this. GNU Radio has a lot of community activities, and you can find a lot of examples of things that people have done. There's several textbooks out there that are good. I have some links later on to other YouTube series which dig into deeper levels of how to do signal processing and people-specific projects. But high school students have used this for science fair projects and all sorts of activities. Moving on from there, we've got down in that bottom corner, a student did their master's thesis on software-defined radio and specifically how to move data around. And for us here in the UK, sadly not this year, but I believe next year, the electromagnetic field camp is always a great event to go to, and there's talks. And I think pretty much every year, one person or another ends up speaking about software-defined radio. There's always an amateur radio contingent there. And so it's a great place to go and meet folks who are doing this. Now, if I'm right, we'll finally get to it. Wonderful. So let's just make sure I didn't skip one there. Yeah, GNU Radio Companion. So that's the big context. I'll show you some of what mechanically makes software-defined radio in terms of samples and pieces through some examples using a piece of software called GNU Radio Companion. GNU Radio itself is a software library written in Python and C++. You can use it directly in your own applications if you're a programmer, but for a lot of people, and hey, for myself as well, even after 10 years of using it, it's really nice to be able to just drag and drop some pieces together, make some connections to say the data should flow through this from this block to this block to this block, connect the steps together, hit run, and just it does it. No code written. And that's what GNU Radio Companion gives us, and that's what I'll be pulling up here in a moment. This is a tool. It generates the code for you, and then it runs the code. This is what the companion looks like just before I pull it up so we can see the labels. We have the flow graph canvas and blocks. This is the main area that kind of everything gets assembled into. Down in the bottom left-hand corner, we have a console. This is a great place to look if something's not worked out. There's often error messages or status messages that get printed out in that bottom corner. Here we can see just a welcome message so far. The variable editor shows some values attached to names there. If you're programmed before, these are your variables. For instance, this one is saying there's a sample rate of 32,000 hertz. This is a very standard audio rate, and so that's the default that GNU Radio will splash down for you. Given that pretty much every radio application needs to know what rate the data is being sampled at, that's always given to you as a default variable. Then finally, on the far right-hand side, we have the block library, and this has a whole list of different blocks that implement different functionality, whether that's an audio source, whether that's a speaker output, a filter. All of these different operations are there, and I'll show a bunch of examples of those. Now, I need to remember when to close my presentation here and actually open up the software. I think that's coming up here. Yes, it is. So you have a bunch of data sources. These are always called source. They're just where the data comes from. Then you have data connections with those black arrows going from block to block. We can see that the blocks have ports on them, the small colored squares, and those that are on the right side are the output ports. They're often labeled out or some meaningful information about what type of data is coming out of there. And on the left-hand side of a block will be the inputs. Blocks can have multiple inputs, multiple outputs, and how those get, what happens to the data from the in to the out depends block to block. This is a flow graph that I'll actually show. So these connections of blocks are called flow graphs because in mathematical terms, this is a graph of objects with nodes and vertices connecting them. We call them blocks and connections, but it's the same conceptually. Data will flow through here, so flow graph. Up along the top of this example are 4 pieces that are called Qt GUI, range, or label. Anything with GUI is your graphical user interface. You put these blocks down and they'll present something to you that you can modify, whether that's a slider, such as these range widgets. You'll hear these called widgets quite often because that's just the underlying programming name for these. Or just a label that's just showing you some piece of information. And I will pull up this graph here in a moment. Yes, so this is the next step once we get familiar with the software. So please do bring questions, throw them into chat as you have them. I do have chat right here on the side, so I'll be monitoring that. If you're on YouTube, as I did see that we should be streaming there now, I will click that link now and be hopefully monitoring chat there as well. Chunk. You have to actually join a channel to join the chat. So sorry, if there's questions on the YouTube side, if somebody can keep a bit of an eye out there, I'll pull it up when I get a break point, kind of 2/3 of the way through, and go back through those if there's anything needed. So, oh, no, that's an image. This is the problem when you take screenshots. Things look the same in the screenshot and on the screen. Yes, I know this thing is being recorded. Let's get stuff out of the way. So here we have the actual running GNU Radio companion. And pull it up. Great. Thanks, Stuart, for keeping an eye out. Here we have the actual GNU Radio companion. I will try and keep these zoomed in so that it's as easy to see as possible. If there's things that you can't see, can't read, just let me know and I'll try and do better. So what are our fundamental pieces? As I said, we have a couple of signal sources. These are generating signals. Guess what? And these are purely simulated signals. In this case, we have 2 cosine waves. Their sample rates are 32 kilohertz, and the frequency of the first one is 1 kilohertz, and the frequency of the second one is 40 hertz. I'll double click on this block and we can see those properties spelled out in a little bit more detail. We have our output type. I'll get into that in, I believe, the waveform demo example, which comes up second. But right now, if you already know the term, we're working with real valued floating point numbers coming out, and that's the orange color of port. We can see our first example of how to use a variable. So in this background corner, we can see there's a variable with the ID samp_rate, and that has the value 32,000. If you see 32K, just keep in mind already that that's going to be a number. It's going to be 32,000, displayed as 32K for ease of use. But if you can't type 32K into the field value itself, that will throw an error. So that variable has the name samp_rate. You type that name of the variable into the field, and these blocks come with it default populated because, again, sample rate is just a concept that's really universal. So why make somebody do the work? what type of waveform. We can put out a constant, a sine, a cosine, square wave, triangle, sawtooth, and these are just the built-in ones of this particular signal generator. I was on cosine, so I'll leave it there. Not that it particularly matters for this example. The frequency of this top block is carrier frequency. Now this may start giving you a little bit of a teaser of where this is going. The amplitude is 1. There's no offset. This is a DC offset from the bottom, and we'll see what this looks like running here in a second. And there's no initial phase. It'll start with a phase of 0. The same thing is configured with a second signal source. The top one is passing through something called a throttle. Now, GNU Radio will by default try and run as fast as possible. Who wants a slow piece of software? But if we're just doing things in simulation, well, the computer's a lot faster than we are. We need to slow it down. And so we say, throttle this, please. Only let through a certain number of samples per second. By default, that's populated with your sample rate variable. And so if we're working at 32,000 samples per second, it'll say, put through 32,000 samples per second. You might want to bump that up or down depending on whether you want to run it faster or slower than real time. It can be convenient to do either one depending on what you're doing. The rule of thumb, which GNU Radio will warn you about, GNU Radio Companion will warn you about, is you want one and only one of these somewhere within a connected set of blocks. It doesn't really matter where you put it. There's some nuances there, but by the time you're hitting that problem and figuring it out, you'll already start to understand some of the reasons for that. Unless you have a piece of radio hardware somewhere in the flow graph, then that will be what slows it down. This could be a speaker output. Your speaker will only output 32,000 samples per second. If you feed it 100 million samples, even if it can store it, it'll just sit there going, okay, well, I have enough audio for the next 2 years. Why do you want to give me any more? I'm just going to sit here and do my job. So that'll give you flow control over that rate of data flow through the graph. Anyways, so these two signals come together, they're multiplied by that block down in the bottom, and then it goes out to a time sync. This is an oscilloscope display. It's just going to plot the values of these samples over time. So let me stop talking for 2 seconds, run this, and we'll see what this looks like. Great. I do not need to see myself 3 times, so that can go away, please. And I will just click on the labels here to turn off those pieces of the plots. So what do we have? We have 3 sliders. We had 3 range widgets. Great. We have a little data display that's mediocrely formatted. That is our label. So we have our 3 QT ranges and our QT label already up there up top. Then down here, we have our oscilloscope type display, and this is data over time. It's getting that time from our sample rate. I'll keep harping on about that because this is one of those concepts which people often get wrong when they're getting started, and after 5 or 6 years as well. Our carrier, unsurprisingly, is just an unmodulated sine wave. This is the one that was sitting at 1 kilohertz. On top of that, we might want to put some kind of baseband data. Now, I'm not doing this for the demo, but hey, next Thursday I'll try and rig this up. You could rig this up to a microphone. So your baseband data could be your microphone audio that you want to put onto a carrier frequency. In this case, it's just a 40 hertz sine wave. So what happens when you multiply a carrier with your baseband? You're going to do some AM modulation of it. And if you combine those two together, I'll turn those back on. We can see that carrier multiplied by the baseband has given us a modulated envelope, amplitude envelope on our carrier wave. Now we can take our carrier frequency and we can start playing with it here. So, if I double the carrier frequency, we can see the carrier has gone up, doubled, but our envelope remains the same. I do have some triggering set up here if you're familiar with oscilloscopes so that this isn't flying by. As I play with these, eventually we will start seeing that carrier actually move. Changing the baseband amplitude, we can see the case as our modulation depth, our deviation gets deeper and deeper. and we reach a point where we have fully pinched off our carrier at that maximum amplitude. Now, as we keep pushing that on, we can see actually a point where we would either be clipping, overmodulating, or just having a phase uncertainty out of this. And so you can get some really fun effects here where you can actually show what these look like as you're going through. Now, if I start changing our baseband frequency, we can start seeing what I was talking about of the carrier no longer being an integer number of baseband lengths. And so it starts scrolling through, but we see, again, the AM envelope remains the same. This is just a really simple example, but hopefully kind of starts showing you how these pieces of GNU Radio come together. My focus again with this talk is really to show you the nuts and bolts and then point you towards that blog post of go and do interesting things with this now that we've gotten past the fundamental hurdles of using the software. So I'll pause for half a second here. And anybody in the actual Zoom call or on YouTube have a question at this point. We will get into more radio applications as we go on, but let's crawl before we walk. And actually, I will ask your indulgence. I'm going to just mute myself for a second and grab a cup of water because I do need that. Okay, now I sound 5 years younger and can keep going for another 3 hours. This is a 4 hour long tutorial, right? So let's get to it. Seeing no talks, great. No talks, no questions, great. Let's keep rolling. The party doesn't stop here. This fundamentally isn't really a more advanced flow graph. I can zoom in a bit. We again have a couple of range widgets. I'm doing an import here. So here's where we first kind of get our slight look behind the scenes. And that doesn't actually get used. I was playing with something here. But if you're familiar with Python programming, you can see here we've said import numpy as np. Super standard piece of Python code. And this is just going to get jammed right into your generated flow graph. What does this mean? Your generated flow graph is actually a Python file. And I'll pull that up in a minute. We can actually put Python code in any one of these fields. So our frequency here could actually be 4 times 4, still 16. No change in the actual value, but starts maybe getting a couple of the brain cells going of, we could actually do something a little clever here, couldn't we? And that's exactly what I've done with this block here. This is a flow graph that I use to show students, often people going through the foundation license actually, kind of what is a waveform? What is phase? What is amplitude? What is frequency? And until you get into some, fairly complicated pieces, phase can look a lot like delay. If you just delay a sine wave, it's the same thing as doing a phase shift on it. So I've put in some Python code that, depending on your screen resolution, may or may not be particularly visible here, but there are slides and we'll get those posted. That just takes the sample rate, divides it by the frequency, and shifts it by a phase in degrees. So when I run this, we can see a couple of things. We have a phase control, a frequency control, an amplitude control, and then a reference signal in blue and a changing signal in red. Great. So as I change the amplitude of our test signal, that second signal generator, we can see the amplitude changes, but the frequency hasn't. I don't actually know why I've split this out into 2 frequency displays, but we get our first frequency display in this. Both of these are at the same frequency. They've just had a phase shift. And so there is a tone appearing essentially at DC. This is showing that it's 500 kilohertz wide from 0 upwards and 500 kilohertz below. We can get into why there's negative frequencies here later. But as I change the frequency quite a bit, hopefully, yeah, we can see. Let me do a simplifying thing here. I know I get in trouble for this, but where is it? Somewhere here, there's a field. Oh, sorry, this is the time sink. In the frequency sink, we only want positive frequencies. I realize I did that fast. I'll point it out a little bit better later. But if I change that frequency, we can see the tone, this second tone on the second channel has gone upwards. If I mouse the cursor over, we can see it's at about 22 kilohertz. And looking up at the actual value here, we can see I randomly slid it to 22 kilohertz and a bit. So unsurprisingly, as we move that across, the tone at the bottom, stop that, the tone at the bottom will move around in frequency. But this example was designed for a very low frequency, so I'll never get it back quite to where it's supposed to be, I'm sure. What was it, 16? Yeah, that may or may not ever quite synchronize back up. But we can play around with shifting phase and frequency and stuff like that. It's a simple, fairly simple example. I'll just relaunch it to show the phase. So we're currently at a 90-degree offset between the reference and that second signal. If I change that to 45 degrees, we can see those two peaks or the zero crossings, whatever you're measuring from, get much closer. In fact, they're half the distance that they were before because we're only shifting by 45 degrees. Just a nice, simple example. And the real punchline here is that you can put Python into any of these fields. So if you've learned to program or you're learning to program, it opens up a lot more functionality in the tool. So where does that get us farther? I'm just thinking, where do we want to jump from here? I'll take a brief aside here and I'll say, look, we've seen a bunch of simple pieces come together. Well, come on, who wants to plot out a couple of sine waves? Are we really here for that? Now, to be fair, a bunch of us have built different oscillators and stuff over the years and said, hey, cool, I can make a single oscillator. But radio, let's keep the eye on the prize and build a full radio. Here on the screen, we have an application called GQRX, which was both written by a ham and is currently maintained by a ham. Alexandru Sest, who I apologize, I can't remember his call sign, but is up in Denmark, in Copenhagen, I believe. And then Clayton Smith, who's a VE call sign in Canada, has been the maintainer of this for recent years. This program, which you may have used or you may have seen, like SDR++, SDR Sharp, what are some of the other good ones? SDR Console, there's a whole variety of these applications, SDR Angel. All of them are fundamentally implementing the same sort of functionality. We're very familiar with seeing a waterfall at the top. We're familiar with seeing an instantaneous signal at the top and some pieces there. So this one just happens to be built using GNU Radio under the hood. It's open source. If you open up some of the files, you'll actually see, GNU Radio block audio source dot connect to a filter dot connect to something else. And it does the big heavy weight of this. From chat, thank you very much. Alexandru Sest, Oscar Zulu 9, Alpha Echo, Charlie, did a phenomenal job launching this and is a great person. So big cheers out to them. Now, I'm launching this off of a file because that's much better for a demo. And here we can see there's a single lower sideband signal nominally at 7.2 megahertz. This is part of something I'll get to towards the end of the talk, where there is a open set of challenges you can walk through, starting with fairly simple and getting up to much more advanced. And this is one of the first ones. Now, I don't know how well audio will carry over. I don't think I'm quite wired up with this. I will see how this goes. I don't know if you'll get my computer audio. You do get my microphone, which we definitely don't need. So hopefully you might be getting computer audio. We'll see. Sorry, I'll do that. The flag is bicentennial. But anyways, yeah, I needed to set that up a bit better. We'll leave that as the first bit of the puzzle, but this is actually saying the flag is, and then a keyword, and that keyword earns you points on the first challenge in this particular capture the flag event. Now, hopefully everyone's seen software like this before. We just have a really simple display of frequency at the bottom, similar to what we were seeing in that Qt GUI frequency sync before. The top has the spectrogram, which is what we get in GNU Radio. There's also a Qt waterfall block that would get you the bottom half of this. Ours aren't quite as nicely styled, but there are plugins you can install to get these. You have some receiver options, all the regular bits and pieces. This is one of the possible end goals of something you could build with GNU Radio. If you wanted to add in M17, if you wanted to add in some custom digital mode, you could take this as your starting place, develop that other piece in GNU Radio, and then plug them together to get you a full application that actually does these. So this is what a very complicated flow graph can look like with a bit of extra custom code to give you the user interface that's really tightly combined like that. So the next piece that I have here, it starts looking at how to bring your own processing in. It's great that GNU Radio brings a whole bunch of default pieces for you. I'll wrap by showing you kind of one really complicated example of that. Let me pull that up. So this is what it looks like if you just jam all of GNU Radio's blocks together. You actually get a full QPSK digital packet or digital modem. This isn't a packet modem yet, but it's one step away from it, and you can follow the tutorial that follows this one to learn how to wrap some packets on this. But there's a full tutorial on this. I won't go block by block, but basically we have a source of data. We have our throttle because we have no hardware. We're modulating this into a digital constellation, and we'll see what that looks like in a minute. And at this point, that's our entire transmitter. It's a really simple one. Transmitters often are the simple half. Our channel model, this is giving us multipath. This is giving us fading. This is giving us random noise. All that sort of pieces can be mapped into this channel model. And there's a couple of different pieces. The European Space Agency actually funded the creation of one for low Earth orbit satellites. So you can actually plug in the 3-letter elements and track something orbiting over, theoretically orbiting or actually orbiting, and get the Doppler shift and everything like that. Once you've received this with a digital signal, you need to figure out, where the zeros and ones are. You need to do some equalization. If things have faded or gotten squished, you need to regularize all that out. And there's a couple of blocks here that do that. There's documentation and tutorials on them. Once you have kind of that recovered good constellation, you can do a decoding step. We'll see what that looks like into a time sync. And then the digital information can be encoded in different ways. This one happens to be differential. You map that out to bits, blah, 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 blah. And at the end, what we'll have here is a time sync with our original data and the data that we've gone through this entire virtual transmitter and receiver. And I'll just run that now. Hey, cool. Crunch, 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 crunch. My laptop's having a little bit of a day of it, but you can see that snap in. The receiver initially had a really broad spread of points on those 4 constellation points. That's because it hadn't tuned in. And you could actually see it correcting for frequency, correcting for phase and amplitude, and it pulled that signal right in to this beautiful set of 4 constellation points. Now, there's some delay of the data being transmitted and the data being received. It started here by saying it takes 50 bits of delay. Looking down at that bottom right-hand plot, we can see the waveforms don't match up. From memory, the answer is about 57 or 58 bits of delay. I'm sure that's part of the puzzle you're supposed to figure out. We can see that's getting really close, but that's not quite matched up, so let's try 58 and let a couple more bits stream through, and it snaps in. So right now, we have almost no noise on the signal. We're getting a perfect bit error rate. There's no bits being dropped. I can increase the amount of noise coming through, give that a moment to drop through. And we can see it's still very easy to make that decision. Whenever you're decoding a digital signal, one of the fundamental question on the receive side is this a 0 or a 1? Or in this case, because we have 4 points, we can encode 2 bits at once. We can count a number between 0, 1, 2, or 3, our 4 constellation points. And that's either our 0, 0, 1, 0, 0, 1, or 1, 1. So we can send 2 bits per symbol, each one of these points. Each individual blue dot here is a symbol. And you can see the 4 places where those symbols appear traced out there. GNU Radio has some tutorials, and I'll link to some good videos on, digging into what are symbols, how do you choose these, and how do those modulation happening. But here we can see kind of GNU Radio dressed to the nines, pulling out the full bit. Take a bit of a step back here. I know we're coming right up at the top of the hour, and I am not done yet. So we got a little bit of a late start. I'll go a bit late, and then I'll hang around answering questions at the end. There's a couple of things I want to get to here, and then a couple of slides. But we're getting close to the main pieces here. Within GNU Radio, we have this built-in block library. I forget if I've installed any plugins. I haven't installed any plugins on this. On Thursday, I'll show you what a bunch of plugins look like. Basically, other people have written other blocks. They've packaged them up, and you can download them as plugins. That works whether you're on Windows, Linux, or Mac. It works best on Linux for the moment, but there's a package called Radioconda, which makes it fairly easy on Windows and Mac as well. So that's great. And also, the Amateur Radio Digital Communications Group in the United States has given us some money and funding. And with it, by the end of this year, Mac and Windows experience should be really top-notch. We have installers and we have pieces that will make it really straightforward. Not the point. So we have these plugins, we have our core blocks, but you've got your own idea, right? I've got my ideas, you've got your ideas. There's that piece of genius that, of course, GNU Radio doesn't have, because it's your idea. How do you get that in here? I've already said that you can put Python into the individual fields, but that's only going to give you so much flexibility. We can do some cool things with like hamlib, and we can control an HF radio from that, but we go just that little bit farther, right? GNU Radio has this piece called the embedded Python block. I haven't actually shown connecting a block, sorry. So if you go up into this core library, I'm going to hit Control F. There's got a lot of Zoom stuff on my screen, but there's this search button here. And we can type in a block name. If I type in time, for instance, we can see under instrumentation, we have that time sync that's been appearing. If I double click or just click and drag that in, we get one of these blocks. We can click and hold an output port. You get one of these connections and drag it in. You can see this one here has a red title. This means that there's something that's going to prevent it from running. So if you have that, it won't run, it won't launch. You can go under help, helper tools, run, view flow graph errors. There we go. And it will tell you, hey, man, you need to connect this port. It's the input port on Qt time sync x_1. If we double click on this one here, we are not showing them by default in my version. The idea of this is that is what was just printed up in there. There's an option as well to always show IDs. And we need to connect to that input port. But I don't need those for this demonstration. But that's how you connect a port. If you pull up a Python block here, drop that in, you can see I have one of these in the flow graph right there. And if we double click on this, it has some example parameter that we can set different values to. But then, hey, it's got a code field that says open in editor. And hopefully I've got that set up. I do. And it's opened up a file here with some Python. And this is what GNU Radio looks like under that first layer of hood. This is the inside of a block written in Python. You can write these in C++ as well, but I won't subject any of us to that tonight. Here we're importing NumPy. This is a number processing library, number Python. Processing library that's extremely standard. It's the lingua franca of number processing within Python. GNU Radio uses it extensively. Then we import the GNU Radio library and specifically the GR portion of that. We'll see GR appear a bunch here. We have a Python class, block, which is of type GNU Radio sync block. What does synchronous mean? It means that when we have one data item coming in, we'll have one data item coming out. In this case, those data items are real valued time samples. So if you have 3.1 coming on the inside, we'll do something to that value, and we'll shove one value out. It doesn't actually have to be the same item, but they'll come out at the same rate. The sample rate is preserved. They are synchronous. You can also decimate, have an output data rate which is lower than your input by some fixed integer. I think integer. Fixed integer rate. Yes, I believe the decimating block has to be an integer rate. The interpolating block, the output data rate is faster than your input. And that is, again, by some fixed integer rate. Now you say, come on, restrictions are not for me. I'm here to hack on this. You've got the basic block. Do whatever you want. Now you have to do some of the lifting of saying how many data items are produced and consumed, but that feature is there if you want to implement complete freeform programming. Those are our four fundamental classes. We have to initialize this. The block needs to know who it is, what its data input and output signatures, what those input and output ports are, and what its parameters are, in some basic setup. That's our initialization. This very common inheritance pattern shows us that the first thing it does in its initialization, it says, we figure that GNU Radio knows what to do with a synchronous block, right? Let's shove the job up there. We're going to call this an embedded Python block. We're going to take in one NumPy complex 64-bit value. So we've made that jump from real valued samples to IQ samples here. Sorry, that kind of happened without note. But we have one port of that on the input and one port of that on the output. We could change this to NumPy float 32, and that would be our real valued floating point numbers. If I wanted to add a second port, I could do that. And actually, let's go ahead and do that. And if I just save that block, all I've done is save the file, and I come back into here, we can see we have our second port and it's back onto that orange color that we were familiar with before. If you go under help types, you'll see the color mappings for all the different basic types. Now, pretty much you're going to see blue, you're going to see orange. Occasionally, you'll see some integer 8s. Those are our bytes, if you're reading a digital file in or out. or sometimes like ASCII letter values and stuff like that. And you'll see messages, which are gray. I almost never see the other colors, but they are supported and they do exist. Let's get back to that file. But I'm not actually going to use 2 ports, so I'll go in and delete that again, save, and that port's gone. We have some example parameter, and it has a default value assigned up here to 1.0. So we take that value that's passed to the initializer, and we store that into something that we're going to be able to use later. If you're not familiar with Python, get familiar with Python, but it's a fairly straightforward language and pretty easy to get going with. And the nice thing about starting this way with GNU Radio and an embedded Python block is you only need to implement a couple of lines here to do something interesting. So what happens when GNU Radio actually launches? I've kind of shown putting blocks in, connecting things, and then I punch this run button. What GNU Radio Companion is doing is it's generating a Python file that contains a whole bunch of these blocks and connections. And then it launches it. And somehow the data starts moving. This is the work that GNU Radio is doing. And it's specifically the GNU Radio runtime is scheduling the blocks to do work. So GNU Radio runtime has a scheduler which knows about all of the blocks, stares at a source block and says, I need data from you right now, please. Work. And it calls this work function. If it's a source block, it won't have any input. There just won't be any data there, and it won't be asking for any. But it'll have this array of output items. And GNU Radio will have said, come on, give me 10,000 values, please. And if it's a basic sinusoidal signal source or reading from a file or something like that, it'll either calculate 10,000 values of the sine wave, or it'll go down to that file, read 10,000 samples and say, okay, get off my back. Here's your output items. And so what we can see here, this simple block is saying on port 0, programming, we count from 0. So that first output port, let's write to all the items are the input items from that first port times whatever this example parameter is. So this is a constant multiply operation. Anything that passes in will be multiplied by our input example parameter and then shoved into the output. And that's the entirety of the work function. The only thing GNU Radio's runtime needs to know at that point is, so how much work did you actually do? I said you could do up to 10,000 items, but were you having a bad day and you only did 4,000? You run out of file, for instance. You reach the end of the file. It says, give me 10,000, and you just stare at it and go, nah, this file's only got 4,000 samples in it. I've read it. I've passed it to the output. I'm going to return 4,000 items. That's all you get. And GNU Radio's runtime will then go, thank you. I know what to do. I will pass those 4,000, not 10,000, to the next block in the row. Ooh. So that's what this block is doing. I don't think I have anything more interesting implemented. The only thing that I've done with this second one is I've renamed it to Coolest Adder, because that's how I get my laughs on a weekend. You can see that this block is gray. It's a good reminder to me. This is a disabled block. It's still in the flow graph, but we're not going to do anything with it. It just sits there. If I right-click on it, I can enable the block, although I apparently didn't actually select the block. We can enable the block. And now you can see those 2 blocks are actually complaining. They're saying, hey, you've got 2 things going into my input. I don't know what to do with that. I don't know what to read from that. We've got some blocks that can mux the signals and take half from one, half from another. That getting well ahead of myself there. If I hit D, that disables that block again. Let me run this. Enough of me talking. Well, enough of me only talking. Here we can see our time domain signal of our inputs, our outputs, and then our frequency domain inputs and outputs. I haven't gone in and labeled them this time, and we're getting IQ valued samples. So if I zoom in, I've just clicked and dragged a box to zoom in. we can see that we have 4 individual signals here. I'll turn off the output values for the moment. Those are signals 3 and 4. This is our input IQ signal. So what we've gone in is we've sampled this signal. That's fundamentally what makes this a software-defined radio. Is we've sampled some time domain signal and we've pulled that into the computer. And all of the actual functionality of the radio is defined in that software. Sorry, it's taken an hour for me to get to that point of actually saying that literally, but hopefully that was in people's minds a bit anyways. We can actually go in, we can go into the settings and we could actually see the individual points, but that's not the point here. One of these is the I, the in-phase component of the signal, and the other one of these is the Q, the quadrature portion of the signal. If you're a math person, you can look up Euler's formula, and you can see that any sinusoidal signal can be represented as A, the amplitude, times e to the j phi phase of omega, which is frequency. So you have a frequency component, a phase component, and j omega t. I'm going to get myself into trouble here because sometimes we mix frequency and phase. But and that can be broken down into a sine wave and a cosine wave. It's one of those nice fundamental pieces of mathematics that you get into with all of this. And I should have a slide. I have slides that show this. And 9 p.m. is not my best hour. So we have our I phase, our Q component of these two, and those are why we have 2 signals. Long way of saying that. Now, if I turn on those other 2 signals, we can see, and I'm just using my mouse and scroll wheel there, the input signals are maxing out at an amplitude of 1, and our outputs are maxing at an amplitude of 2. We have successfully multiplied by 2. Now, here's a fun one. What does a multiplication of a time domain signal by 2 give you in power in decibels? So we have doubled the voltage equivalent. And here we can see our 2 power signals sitting right at 1 kilohertz here. It's a fairly coarse discrete Fourier transform, so we're looking at a coarse piece of the frequency domain here. But we can see that our red output is very clearly above our blue input. And if math works out, this should be 6 decibels higher. We've doubled our voltage, which means that and the power is the square of the voltage. So 2 times voltage increase gives us 4 times power increase, means that we have doubled and doubled again, 3 dB and 3 dB again. 3 dB gives us a doubling of power. Depending on your background, I'm either completely overloading you or I'm going too slowly. Hopefully, most of us are somewhere in the middle and everyone's having a bit of fun. Now, where does that get us? Thanks, Tom. So, great. That's how you can jam some of your own Python in. Now, I hope some brain cells are going. I hope some people are going, oh, I wonder what I could do with that. I have this one thing I've wanted to do. And that's basically what we're going to do on Thursday, is run through a couple of these examples. I have blown through my time, so I won't pull up my HF radio today, probably. But one of the things that I'll show on Thursday is I have a Kenwood TS590S HF rig, and it has a USB cable that you can plug into it for computer control. And it gives us a sound card input and output. We can drag those sound card inputs and outputs into GNU Radio. We can drag the computer control in via Python and the hamlib library. And without having to go and find new blocks, with a few lines of code, we can actually create our own source to control the radio in frequency, read what frequency it's tuned to, and show a basic spectrum plot to get a pan adapter style view of where the radio is tuned. But we're going to have to leave that for Thursday. So we've got our first real comment. So M0JQQ wants to display various signals through an SSB transceiver for your online training. Chances are that some piece of this would be able to do what you want, depending on exactly what it is that you want to do. Something that I've done in a classroom before is have students using pre-recorded files with GNU Radio and with SDR++ and other applications like that to view the signals and be able to tune around, get a feeling for what it sounds like to be a little bit off, high and low, and you can visually see that you're high or low. And that's really made a lot of things click for students that otherwise can be a bit of a hard thing to grasp initially. And you can do the same thing actually where the instructor is live streaming data out over the internet, and each of the students can zap into a feed of that and do some signal processing on it. If those are things that people would like to explore, we can do Thursday a bit more open-ended, particularly if people throw questions into the SDR chat room on the online amateur radio community Discord. We can try and prep some things in advance or put together some ideas. I'm going to skip the Python messages for the moment, at least the details of it. I'll just show the basic idea that if I, say, hello world, hello ARDC, this is a string message. I hit enter and it just kind of vanishes. But we can see that I have a file sync here, and that's going to my desktop with a file called message output. If I still have an editor open and I open my desktop, message output, we can see hello world, hello ARDC. So that message is a non-streaming bit of data that's gone through the GNU Radio flow graph and gotten written out to a file. This can be something, there's some great examples of sending like APRS packets or RIDI packets where you type in a message and then the modulator actually encodes that, turns it into bits, modulates the bits, and sends that packet out. As for instance, audio that could go on to a single sideband radio connection. Now, let's take a breath. That's a lot of GNU Radio. That's a lot of code, depending on what your level of familiarity is with all of this. I've hit the wrong button. We get to see the beginning half of the presentation again. And if we roll through all of my nice slide animations, we get to here. So we've just brought our own signal processing into there. And as you see, right-click to enable, disable, or bypass, or use the E, D, and B keys. Bypassing only works if you have one input port and one output port. It will just automatically connect through. Anything more complicated than that, GNU Radio goes, man, I just don't know what you mean. This is the template for that embedded Python block that we just saw. So if you're watching the audio recording, the recording of this talk, or you're here live and you catch the slides, I walk through more of the meaning of what each of those sections was like. So like, for instance, the red sections are Python comments. The template has some decent ones. Always comment your code, because I guarantee that in 4 weeks, you won't know what you've written, much less anyone else. So this is a slightly modified piece. In today's example, I did multiplying by 2. You can also do DC offset. That's the test setup. So pretty much exactly what I had that we were seeing here. And the only difference is that we're more explicitly dealing with the IQ portion. And we're saying, let us take the input items and add to them an IQ value, a complex sample that is composed of the DC term, our example parameter today, plus that example parameter times 1j. Let's make it that Q component. This is an imaginary number There's nothing imaginary about them. It's a complex number. There's nothing really complicated about them. These are terribly named. Uh, it's just a two-part number. It's got some very simple math behind it, and the naming has done more to make this confusing than anything else. But if you want to install GNU Radio, if you're on Mac or Windows, use the Radioconda installer. The GNU Radio wiki has links to all of this, and I have that in the slides here. Try running this. Try putting this together and try doing this as your first bit of Python coding with GNU Radio. Here's the results that you get with that. You can see that instead of changing the amplitude of both halves, it's simply elevated two of those signals slightly up. That's our DC offset. What is DC? DC is energy at 0 hertz. So as we move our tone around, that little DC offset is going to present as energy in the frequency domain at 0 hertz. Given the way the discrete Fourier transform works, it's centered around 0, and so this spike in the center is our DC energy. This is a piece that I will leave for Thursday. You can run GNU Radio Companion and stuff like that in a Jupyter notebook, and we'll go through there. And I think, to be fair, I will leave a bunch of this for Thursday. There's some cool ways of storing files that I just want to make people aware of. There's a great blog by Daniel Estevez, EA4GPZ, I believe is his call sign. But he has a phenomenal blog and goes very deep into signal processing. It's what happens when you have a math PhD, I imagine, but he is the most friendly person in the world and publishes up some astonishingly good blog posts with all of his source code, with all of his source files. He's currently working his way through LTE and 5G, explaining those waveforms. And here you can see a 5G recording, PDCH, with some of those signal blocks highlighted in there, and that's a factor of how this file has been stored and commented with these annotations. For people who have explored some non-amateur radio signals, this is a LoRa signal here. We can see that, well, maybe we can see that there's some horizontal chirps going on in here, and that's a property of its modulation scheme. A whole bunch of Bluetooth packets being spread out over the 2.4 gigahertz band. LTE uplink, again, spreading energy over 1800 megahertz. This is a US recording. We get it in a different band here in the UK. And some links to this file format. Probably of interest only to a very few people here, but I'm hoping that more people will record data in SIGMF because it does some really nice things like tell you the sample rate that the file was recorded at. If you don't have that, your recorded file is meaningless. I'll go through all of that later. So this is what I want to really leave you with, is capture the flag. This website is up and running, and you'll see that this is the 2024 version. There is 23, 22, 21, and I think even 20 might still be online. And this is a nice set of challenges. So your goal with each of these challenges is to find some secret code that's hidden somewhere in the spectrum or in some bit of a puzzle. This particular example is not one, unfortunately, that we can do because it was an interactive one run at the GNU Radio conference. But they actually did Wordle on 915 megahertz on the air, 926 megahertz on the air, and you had to send APRS packets back at this, also in the ISM band, to complete your Wordle. So VE3 IRR, Clayton Smith, who wrote GQRX, as I mentioned earlier, created this particular set of challenges and has been running the challenge. So you could send a tone as your first guess, for instance, and see that the A was correct. Flare, caulk as a correct one, and that gave you that. So that was a really great hands-on piece that had a lot of people learning. On just a fun note, the GNU Radio conference always runs an amateur radio exam, and we've had upwards of 50 people get licensed per conference, which has been great fun. But there are a whole bunch of challenges here that you can still participate in. So go check out this link. They do start genuinely from like, what frequency is the tone on this file, or what does the FM voice say in this? And so it's just, can you install like SDR++, can you install GQRX and open a file? That's the level it starts out with. At conventions and stuff, this is a slide that was meant to go farther up, really, or kind of a repeat of what we saw earlier. At cybersecurity events, there's often a very large SDR area and workspace. This is the Signals Village from Black Hat, I believe. And so you can see a lot of people playing with these things. This was out in Germany a couple of years ago. The Chaos Communications Congress runs a summer camp, very similar to our electromagnetic field, except about 5 times larger. And those always have really good radio tracks and stuff like that as well. These slides are really sitting there to try and get people who haven't already seen amateur radio and wireless and hacking and stuff like that and say, no, this is really cool. It's really fun. I certainly have never regretted it in the last 15 years getting involved. This was actually from one of those camps. They handed out, every attendee got an SDR receiver based on the HackRF. And so the badge for the conference was actually a HackRF receiver and transmitter. Again, something to cover later, but Daniel Estevez has been doing some really fun bits. This is where to go to find all those plugins. CGRAN is the website, cgran.org, the comprehensive GNU Radio archive network. Thanks to some old programming languages and cultures, we got that as a naming. But there's DVB-S2, there's Zigbee, there's GPS, there's ADS-B if you want to do plane tracking and decoding, a whole ton of things there, and a bunch of ham modes as well. And we'll look at some of those on Thursday. Here's the real punchline. Thank you for sitting here for an hour and 20 minutes or so. The punchline here is go and check out some of these. GNU Radio has a bunch of tutorials. Thanks to ARDC, we got a grant. We just improved a bunch of the tutorials. So if you looked at them a couple of years ago, they are better now. The second one here, though, is a full YouTube playlist. Professor Jason Galuccio at Harvey Mudd in California just made this for his students. It wasn't actually part of a course. It was just something along the side for his students. And this is about 14 videos on YouTube using GNU Radio, walking through a few of the pieces of what I've done here, but also explaining sample rate and receiving and how does a filter work? How do these various pieces of digital signal processing work? I haven't repeated that because he does a better job. AGISETI.com is for radio astronomy. If you want to, receive some signals from like the Milky Way arms or pulsars, there are pre-recorded files, full lesson plans, full descriptions, and the sample files. They're provided by the SETI Institute. It's aimed at community college teachers to integrate into their courses, but hey, nothing saying that we can't take advantage of it. If you already program, if you've done some Python, or at least are kind of really interested in learning Python to do signal processing, pysdr.org is a great website. It leans into GNU Radio towards the end, but most of it is just straight Python. Let's explore the basic concepts from a computer-first perspective. Daniel Estevez, who I've already mentioned, has GNU Radio tutorials up on YouTube. Just search Daniel Estevez, GNU Radio, you'll find them. GNU Radio Project has its own YouTube channel, GNU Radio Project, and it has years and years worth of conference videos and workshop videos that are up there. Not really beginner tutorials, but there's some material there. Hit the other ones first, go on to the conference later. And right, I'll mention this now. The SETI Institute has been the partner of GNU Radio for a number of years now. So big thanks to them. They've handled all of our finances and logistics, help us run the conference, get the grants, and they do a bunch of the educational and outreach pieces. This is a photo of 3 out of their 42 6-meter dishes that they have in Northern California. that they have graciously allowed many members of the GNU Radio community to get time on. So we pointed it at the moon and looked at a microwave contest, for instance. And other bits of citizen science have engaged there. So if you learn GNU Radio, there's the ability to stream data from this if you have a project idea and kind of propose it. This is the grant that we got. It's been amazing to have this, and the timeline's been slightly extended because some of these turned out to be hard problems, but the documentation, the examples, the tutorials, all of them are much better thanks to ARDC. These are some of the companies that use it. I kept this in because I want to kind of ram home the point that this is not a toy. The fact that we get to use it as one is amazing, but there are big companies using this as core pieces of their infrastructure. So it's a very powerful tool. And if you're a student, for instance, or somebody who's job hunting, I can guarantee that if you know GNU Radio and maybe are willing to move, there's people in the UK who will hire you instantly based on a bit of GNU Radio and signal processing experience. It is a very highly demanded field. I work fully remotely for a company doing GNU Radio development and signal processing. This is when our next conference is. Hey, if you want to fly out to near Seattle, Washington, by all means, please do join us in person. But we also live stream all of it on YouTube. So you can register for free for virtual attendance. Done. Under an hour and a half. Here's some of my email links. I am on the Discord. OARC, Online Amateur Radio, yeah, OARC, is my main amateur radio organization within the UK. So I hang out there pretty often. Hit me up in the SDR chat room. GNU Radio does have a Discord as well. I'll post a link to that. Please come try things, ask questions. If you're a student, I'll make one final pitch, which is that we have paid summer internships. There's several £1,000s to work for a number of weeks with GNU Radio mentor on a specific signal processing or software challenge. So that's my last pitch. Thank you very much. Our next meetup will be on Thursday, which is April 3rd at the same time, 8 p.m. London local time. And I look forward to seeing people then. I will stick around and answer questions, but that's the end probably of our main discussion. Well, not discussion, me talking at you. Thank you.
Awesome, Derek. I'm going to jump in and say thank you very much indeed. Great talk, really good quality. Great for anyone to get a foothold in. A couple of quick questions selfishly from me. First one, is there like an authoritative wiki or like a central reference library for the blocks specifically? I apologize if I missed it earlier. Yeah, and so there's a breakdown of all of the standard blocks built in and what they do.
That is correct, and you don't have to go hunting. If you open up GNU Radio Companion, you double click on a block, there's a documentation tab. We used to have documentation in here and nobody would edit it there. So we stuck it on a wiki and just put a link in. Cool. So if you just pound that link, it'll drop you onto the page. Awesome,
thank you. And secondly, a bit more whimsical. Are you aware of anyone who might have done any experimentation using like an LLM to like do anything with GNU Radio, really, like around designing flow graphs or blocks or whatever?
Absolutely. ChatGPT is moderately competent at spitting out both full GNU Radio flow graphs and individual block code. Like any LLM and any code, it gets it wrong. But you know, if you have a prolonged discussion with it, it'll generally hand you something that does what you have asked it for. Just ask it the right questions.
Awesome. Thank you again so much.
Yeah, definitely. So that's on the LLM side of things. I will use that as a small jumping point to say there's also a very active group of people and companies and organizations integrating AI and machine learning into wireless communications. a lot of that foundational research was and is done using GNU Radio. So if you look up some like RF machine learning data sets, many of those that are public are generated using GNU Radio. There are whole textbooks on this, machine learning and wireless communications. I do not recommend this book for a beginner. Do not buy this book if you have not already done a bunch of wireless comms and a bunch of machine learning. Ask me how I know.
It's an obvious fit though, right? The two domains together.
Yeah. So it's actually now my full-time job as of 2 weeks ago doing RF machine learning applications. We're doing signal identification. So is there a signal here? What is it? What type of signal is it? And then even going further than that and saying, well, okay, why can't we just attach AI to the actual transmitter and receiver and say, come on, you can do better than our coding, right? Guess the symbols. We'll give you some hints. We'll give you a whole bunch of training data, but then just go at it. And it can do some really cool things. If you've ever heard of digital pre-distortion, when you transmit a signal out of a radio, one of the first things that happens is you'll generate a fairly ideal version of your signal, and you'll run it through an amplifier. And those amplifiers are nonlinear. They heat up, they cool down, they, squash the highest amplitude portions of your signal, all sorts of effects. And you can digitally modify your input to correct for that. Or you can just attach an AI model on it and just say, come on, make the output look like a big version of my input. And it just learns the entire piece. And it'll learn the full path on the side as well, whatever the atmosphere is doing. And there's some great papers published about that.
So this ICOM 7300 next update runs on FPGA.
Yeah, people are putting it on FPGAs. There's a lot of GPUs burning a lot of heat doing this. There's some really cool dev boards, if you're looking to spend money. NVIDIA in December announced something called the Orin Nano Super Dev Kit. It's 250 quid, and it has a really competent processor on it, as well as a really competent GPU equivalent for doing AI and machine learning type coding. It's kind of like a really, really powerful Raspberry Pi for these sorts of tasks. Not cheap, but cheap on the scheme of things.
Anybody else got any more questions?
No, I'll just say it was very interesting. I've downloaded GNU Radio Companion. I'll start playing.
Excellent. I do totally recommend that both the capture the flag is a great fun bit just to like have some puzzles to solve. It's always nice to have a point to what you're trying to do. And at the beginning, it can be really hard with an SDR to go from that initial piece of how does the tool work and my great big idea on the end. There's a learning curve. There's no getting around that. Just like when you're learning circuit design, or just when you're learning antenna design or something, there's a long way between your first dipole and how does Yagi work. And that 50 things to do with SDR was the other one.
Problem. If that's everything for everybody, we'll stop the recording and stop the live stream, and then everybody can chat at their heart's content.
Great. Thanks, Stuart.